understand how galaxies form? Can I understand what the black holes did to the universe around them? How did they shape everything? How did these structures that, that I just described as filaments, how did they come about? How did we go from tiny little ripples to a universe that looks incredibly structured and organized, and as galaxies organized like necklaces on a jewel, as I described earlier? So let's go to the next slide. So the question then, one of the questions that comes up is, but why? We can observe the universe, we've seen what it is like, so why do we need to do anything now? And the answer is, if I was to take an image, and this is what astronomy does, it takes images of the universe at different times, and you see change going from one place to the other. If you don't know what the change, what's caused the change, if you don't understand the physics, if you don't understand the astrophysics, you're not going to be able to figure out how the change happened. So to illustrate that, consider this image. This is an image of the Arctic, of a region in the Arctic taken 103 years apart. So this was about 103 years ago. You see glaciers filling this landmass right here. And then today, if you were to take that same picture, this is what it would look like. So having two different pictures doesn't tell you what happened. Okay, you can say the ice melted, but how did the ice melt? Did it all melt all together really fast, like in 6 months? Or did it happen gradually? In order to make sense of that, we have to understand the physics. So the challenge of people like myself who are astrophysicists is to understand how all this happened. How did this change actually occur? Okay, let's go to the next. So the starting point is we know that there is gravity in the universe, and we know that matter responds to gravity. So that's the very first thing. And so what we do is we can take a huge box and fill it up with matter and make it, sort of look like the universe, and then just simply put it on a supercomputer and let the particles respond to gravity and move around, and they'll speed up and they'll organize. And we can ask the question, what happens if you do that? Now, as I said to you earlier, we cannot go back and press restart. We cannot set the Big Bang in motion again. But what we can do is we can put this on a supercomputer and repeat this. And just as Europe and North America, Canada, United States are in the game of doing this, so is India. India has gotten some of the fast supercomputers over the last few years, and there are a huge number of astrophysicists who are working on these problems. One of the reasons why I'm at IISc is because I'm working with a collaborator who's one of the world's leading experts in this area. Together we are able to combine our expertise to push the field forward. So, again, I emphasize that not only is the education here excellent, you have some of the best universities in the world, and the research that's being done here is right up at the cutting edge with LIGO, with the 30-meter telescope. There is a huge scope of opportunities available all around. And now the question is, if you start with this box and you let it run, and you let it run for an equivalent of 13.7 billion years, which is the age of the universe, what happens? So let's go to that. So this is a box. Now, can you go back before and not start it first? Can we just back up? Yeah. Go back one slide. Yeah, right there. Just stop it. Okay. Now, I guess it's starting on its own. If the box was stationary for a second, you would have seen that there were these blue smudges. Those smudges are regions where the ripples are a little bit stronger, and then the black regions are ripples are a little bit weaker. And now you let gravity start moving, doing this magic. Can we just repeat this slide again? Yeah, so you can see these ripples. These ripples are slightly blue, and now you let it start running. And what you see is regions where their ripples are a little bit stronger. There's a little bit more gravity. And they start pulling things together. And so as they pull things together, that region becomes more and more dense. And if you do this over 13.7 billion years, or in this case we stopped it at 11 billion years, what you see is a universe, virtual universe, that starts to look like the real universe. It has matter that gets organized into filaments with galaxies strung out along the filaments. And then you have voids and you have regions. Okay, can we play this again? Great. So you can see the structure starting to form, and you can see these spaghetti-like filaments starting to form throughout the universe. And then where the yellow dots are, that's where galaxies and clusters of galaxies are starting to form. So we are, with ordinary matter and just gravity, we can actually start to form things that resemble the universe. But there is a little hiccup here. The hiccup is that universe doesn't just respond to gravity. What I'm forming is stuff that looks like a galaxy, but it doesn't really, resemble a galaxy. If I want to make something that looks like a galaxy, I need to throw in a little bit more physics. Now, you're familiar with ordinary matter like ourselves. The room is full of ordinary matter. You and I are made of ordinary matter, and we are radiating. If you touch your head or your hand, you'll see that you're warm. You're radiating energy away. This is why ultimately you'll get hungry, and then you'll have to eat to replenish the energy that you're using. You will move around, and you will use up energy. So we have to worry about this extra physics that's coming in, where as matter comes in and it radiates energy, what happens? It cools down, it heats up. How does that change everything around it? So let's see. Okay, so first of all, before I even start complicating things, if I just take the image that I just made, the box, and I make a map of it, and I compare it to the real universe, I think you will find that you are hard-pressed to tell the difference between these. These two here are simulations of the kind I just showed you, and these blue maps are real universe. So the large-scale structure of the universe is coming out right. We can get that much just straight from gravity and the ripples that we have observed at the beginning of the universe. Okay? Now, let's go one step further. We know that the universe isn't just made of stuff that responds to gravity. Stuff responds to radiation. Ordinary matter like ourselves, when you squeeze it, it heats up, it radiates, it cools down, it glows, it has pressure, right? When you fill up air in the balloon expands. In the same way, all of these processes have to be accounted for. They all play a role. So let's go to the next slide over. So what I want to do is get to this. I want to be able to make a galaxy that looks like our own galaxy or like this, our nearest neighbor galaxy, Andromeda. Let's go to the next slide. And the amount of physics that I have to put into the simulations now becomes infinitely more complicated. First of all, the number of physical processes has already grown.